Just admitting a few more people. Great. So welcome, everyone. Thank you very much for coming to this week's paper club. And today we'll talk about a paper called ReFT, or Representation Fine-Tuning for Large Language Models. So this paper is by authors from Stanford, and it proposes a new sort of parameter-efficient fine-tuning paradigm for large language models. So I chose this because it's quite a unique approach, and it's almost like a completely new way of fine-tuning models. It has a quite interesting premise and the intuition behind it, which is sort of rooted in AI interpretability research. So yeah, I just thought it's a quite cool paper to present. So what's the high-level problem that it's trying to address? It's that fine-tuning models towards some given tasks is expensive and it takes a long time, and it also occupies a lot of memory. So there's several methods that have been proposed to kind of tackle that. The most, I guess, popular one is parameter efficient fine-tuning. So these are the sort of methods like LoRa, where we're trying to sort of limit the amount of weights that are being fine-tuned towards a given task, and therefore we reduce the overhead associated with fine-tuning. But however, most of those methods are operating on some kind of weights of the model, either the original ones or some additional ones. So the problem is that we need a method that, first of all, achieves the same or better results. It doesn't need as many examples to train, and it takes a shorter amount of time to train. So at a high level, the approach is to instead of fine-tuning the models by adapting their weights, we modify the internal representation of the model during inference. And yeah, as I mentioned, this approach is rooted in interpretability research. And yeah, and it had some quite interesting results as well. A few state-of-the-art results on popular benchmarks, some negative results, which I'll talk about later. But it's kind of positioned as a beginning of a research area as opposed to like an incremental work. So there's much more work needed on like hyperparameter tuning and sort of tweaking this method to be better. What's really good about this is that they've released a library for this method. It's called PyReFT, and they'll leave a link here. And I tried it. It's quite easy to use, and it seems to produce quite good results as advertised in the paper. So yeah, I would encourage you to have a look at that library and play around with it. It's quite cool. So I thought that before diving into the paper, I wanted to sort of go over the current space of fine-tuning to sort of explain how we sort of arrived at this point of representation fine-tuning and why, and also kind of explain the motivation behind this research. So, so I compiled a bit of information about like the usual methods of fine-tuning models. So the first one would be like full fine-tuning or supervised fine-tuning. So in this method, we basically update all model parameters by training it in a supervised fashion towards a given task. And I guess the downside of that is that during training, it requires a lot of memory because we need to store all the optimizer states for all the end parameters. In some cases, we also need to store things like momentum and variance depending on the optimizer. And the speed is slow because we have to calculate all gradients and all activations, which therefore costs a lot of money and energy and sort of compute time. So in terms of performance, that's where we can achieve the best performance because we can update all of the weights of the model and fully adapt to the task. And also at the inference time, it's not really affected by this. It's behaving the same way as the base model because we modify the weights. And memory is exactly the same as the base model. So another approach is to do prefix tuning. So we would keep the base model parameters frozen, and then we would prepend a trainable prefix token vectors to the input embeddings at each model layer. So this reduces the amount of sort of trainable parameters that We have to adapt during the process, so it's lower footprint and it's faster because we're only training those select parameters of those prefixes. There's some minor overhead in terms of inference, but not much. And the performance is lower than the full fine tune because we cannot make use of all of the parameters of the model. But it's quite effective when the task only really requires to reshape the existing knowledge within the model, or rather to condition the model to focus on something specific. So let's say we have some information that the model already contains within its weights or concepts, and all we want to do is just reshape that output into maybe something like a table or a JSON object or something like that. So prefix tuning is quite good for that. So yeah, this is kind of the diagram of how that works. So looking into the attention module of transformers, we would have a down and up projection sort of module that produces an embedding for a prefix, which we then prepend to the value vector for the key and value vectors here. So yeah, that's how it would work. We would then train the weights for how do we embed that prefix, and also the choice of a prefix is quite important. So next one will be adapters. So again, we keep the base model parameters frozen, and we insert small trainable neural networks between the layers within the model. So typically we would do that after the feed forward in each layer of the transformer. So again, in comparison to the whole model, which usually can contain into billions of parameters, the adapters are quite small in terms of the number of parameters that they have, usually about 1% of the total model. And therefore, it's relatively low footprint in terms of training, and it's faster than the full fine-tuning because we can keep all of the parameters of the models frozen, and we only update the parameters of the adapters. So inference, ever so slightly slower than the full fine-tune because we need to compute the adapters, and memory as well because of this minor overhead of these additional parameters. Performance, again, it underperforms full fine-tuning, and it allows for multitask learning by essentially swapping the adapters without retraining the base model. So we could have an adapter fine-tuned towards some task, like English to German translation, and we could swap it out for another adapter that allows the model to, let's say, translate from English to French instead. So that's how it would logically look like in terms of the model architecture. So we have some feed-forward layers within the transformer layer, and we would insert these trainable sort of neural nets in between those. So I guess we're sort of moving into the area of parameter-efficient fine-tuning, and I'm sure many of us have heard about this technique called LoRa. So LoRa stands for low rank adaptation, and the idea is somewhat similar to the adapter. Sorry, someone just trying to join. Yeah, so the idea is quite similar to adapters. But instead, we introduce trainable low-rank matrices that are sort of combined with the base model weights to produce the hidden states of the model. So for each weight matrix in the model, we would add two matrices, so A and B, and those would be like the down projection and the up projection. And therefore, we reduce the number of trainable parameters because those are lower rank matrices. And we can adjust the rank of these matrices, which then allows us to tweak the performance of the LoRa adaptation. So if we pick a lower rank, the information will be more approximated as opposed to a higher rank. Memory is quite low footprint. You only really need to store the activations and the gradients for the low rank matrices, and it's faster than a full fine-tune as we only really need to update these low rank matrix parameters. Inference speed, ever so slightly slower than full fine-tuning, but what we can also do is we can merge these low-rank matrices into the original model weights, which basically turns it into a full fine-tuned model, not in terms of performance, but in terms of sort of speed and memory. Performance, it is comparable to full fine-tune in many tasks. Some people argue that it's worse performance than full fine-tune. It's kind of depending on opinion at this point. And yeah, as I said, the rank determines the performance. So the idea here is that, yeah, we also have these additional weights that we sort of keep together with the frozen weights of the model, and then we sum them up to produce the hidden representation here. So we've got the matrix A and B, the down projection, the up projection. So I guess the state of the art at the moment is something called DORA. So this is a weight decomposed low rank adaptation. So it's an iteration on the idea of LoRa, where we keep the base model parameters frozen again. However, what we then do is we look at the weight matrix of the model, and we split into the magnitude and direction components of that matrix, of those vectors. So it's similar to LoRa, but we introduce the low rank matrices for the parameter update, but only to the direction components of the of these weight matrices. So it's a simplified solution space when we think about like how we have to adapt these parameters compared to LoRa. So at the moment, this seems to be the state of the art in like parameter efficient fine tuning. Memory comparable to LoRa. Speed is slightly faster than LoRa because we have less parameters to update. We're only looking at the direction components. And yeah, inference slightly slower than full fine-tune, but we can also merge them, same as in LoRa. And there is some minor overhead in terms of memory, again, if we don't merge it. So yeah, better than LoRa. Tunes the magnitude and direction separately. I forgot to mention that the magnitude also gets tuned, but in a slightly different way. And it allows for more fine-grained adaptation. So it only focuses really on the most impactful elements of these weights. So this is the sort of logical idea behind this method. You know, we split, we decompose magnitude and direction. We then adapt them, and then again we have two low-rank matrices that adapt the direction component. This is an interesting graph here, which I found in the DORA paper. So they looked at the specifics of the magnitude and direction of like some select weights within these models, and they wanted to compare full fine-tune, the LoRa and DORA. So you can see that when we look at the magnitude and direction of the weights in LoRa, of these low-rank matrices, it's almost a completely different story compared to the full fine-tune, whereas DORA almost follows what the fine-tune does. So it's a method that provides closer performance to full fine-tune compared to LoRa. So now what I wanted to talk about is I guess the intuition behind ReFT and this representation fine-tuning, and how the authors kind of came up with the idea of representation fine-tuning. So in the area of explainable AI, there is a methodology called causal abstraction analysis. And essentially, it's like a theoretical framework that tries to align together a high-level causal model. This could be like a symbolic model or a way of understanding a concept to a low-level deep learning system. And it is typically used in explainable AI to try and determine how different parts of a neural network encode concepts within the neural network. And we can do that by looking at a high-level sort of causal model of the concept, and then we try and align it together with the low-level model. So this is an example of this, where we have like a causal model that looks at a Boolean operation. The Boolean, you can see the truth table on the left here. And basically the operations are that if both inputs are true, the output will be true. And in all other cases, it would be false. So this is kind of the logical high-level model for this causal abstraction of a concept. We can also train a neural network or a simplified neural network to basically ideally perform this task. The weights that basically achieve this are this. So we've got some of the weights for the weight matrix, weight vector 1, weight vector 2, some additional weights here, plus the bias. And the idea is that if both inputs are 1 for this neural network, and the output is higher than 0, then the logical output of this network would be true. In all other cases, it would be false. So essentially, what we're trying to do in causal abstraction analysis is to align these two representations to then affirm that a certain high-level concept maps to certain variables in a neural network, and in what way it does map within the neural network. So one way to perform this analysis is to use interventions. So an intervention is essentially a specific setting of the model variables for both the high-level model and the low-level model. And yeah, and they can be defined on both of these models. So here again is an example of this. So say we have an unintervened model, just a high-level causal model, and we have an input of false and true, and in this case, the output should be false. But we can intervene on this model, which means we could fix one of those parameters of that model or variables to true. So say we fixed v1 to true. That would mean then that the same input would produce true instead of false. So it's an intervention on how that model operates. We could then perform the same thing on, or an equivalent thing on the low-level model. So in this case, on intervened network, if we have an input of 0 and 1, these would be the states of the hidden variables, and this would be the output. It's less than 0, which means it's false. So we could also intervene on that. So we could fix one of those representations or hidden variables to say this number, and we could force that model for this specific input, which is 0, 1, to then output true. So that's how we would understand interventions. So what is causal abstraction alignment? So say we ask a question like, does this low-level model implement the high-level causal model? And this question has to always be asked in this analysis relative to the specific alignment of the variables between these two models. So what we're trying to do is we try to infer a relationship between some set of low-level model variables and one high-level model variable. So we're trying to find a function that maps these these low-level variables to values of an aligned high-level model variable. So these we could infer kind of manually just by looking at them, or some of them have to be discovered. And essentially, we can do that, but we can perform this alignment iteratively by performing these interventions. So sure, thanks, Lewis. So one of those interventions is called an interchange intervention. So say we select a target variable. So for example, the same example. So v1 for the high-level model and h1 for the low-level model. What we then would do in interchange intervention is we would process two inputs. So a base input and a source input. So base input would be some input that produces some output. So for example, the two inputs for the two input variables would be 1 and 1. And we would expect the high-level model to produce 1. We also would expect the low-level model to do the same. And then we produce an input that produces an output that is counterfactual to base, which means the simplest input we could figure out for this one is that it's 0, 1. So we know that this would produce 0, which is counterfactual to 1. And then what we would do is we would intervene on both these models, so on the high-level model and the low-level model. So when we process the base input, so in this case 1 and 1, we would then process the source input by both models, and then we would take the representation or rather the value for the target variable from the source, and then fix the base to that value, which means and then basically do the opposite for the opposite, which we would do the source when we run the models through the source. We would replace the target variable value with the base equivalent. And then we would observe how both of these models would change. So if we have an alignment between the set of low-level variables and the high-level variable, both models should produce equivalent output under this intervention. And then what we could do is we could propose several of these alignments after interventions. Rather, we could propose several of these interventions, and then we could measure an overall score or accuracy of this interchange intervention. So if it's high, then that means that the low-level model implements this high-level causal abstraction. So this is how this generally happens in sort of explainable AI. And I guess the next bit would be there are some issues with this, because we would traditionally assume that high-level variables align with disjoint sets of these low-level variables. So some concept would be implemented by disjoint groups of neurons in a neural network. So there are some risks with that sort of thinking, because we may have chosen a suboptimal alignment, and it may be wrong to assume that this relevant causal structure will be encoded in the standard way we think about or assume about these models. So here we've got an example of that. So say we perform the interchange intervention, where we replace the base target variable value with the source variable value for the high-level model, and then we try to do the same thing for the low-level model. We observe that it doesn't produce the same output. So in here we would basically move the 0.6 to the 0.6 for the base. So it doesn't work. It seems like that there's no alignment, but we could simply rotate the H1 and H2 in a vector space by -20 degrees. So if we go back to this, you can see that the perfect weights for this model to implement this high-level model are these, and we could achieve the same intervention by rotating it by -20 degrees, which flip the behavior of the network. And that actually achieves the behavioral and counterfactual accuracy. So there is alignment, but it's not in the basis that we chose or assumed. So therefore, the thinking should be, I guess, is that there might be many-to-many mappings between the high-level variables and the low-level variables. So for example, artificial neurons would play different roles depending on the concepts that they collectively encode, as opposed to those being disjoint groups of neurons within the network. So one way to do that would be to transform these sets of variables to some vector space, and then perform the interchange interventions on some orthogonal subspaces of the vector space. And then we transform it back to the original representation space of the variables. So traditionally, this would be done using brute force. So you would search through this discrete space of alignments and interventions. So it's quite slow and complex. But I guess what the newest approach to this is we perform distributed alignment search, which is actually used in ReFT to modify the adaptations to representations. So we know that the alignment can be achieved more easily when we look at them in a different basis. So the new way would be to freeze both models, and then we define some sort of training objective for the interchange intervention. We'd produce some orthogonal matrices. We would then parameterize them in a differentiable way, and then we would simply use stochastic gradient descent to optimize towards that training objective for the interventions. So the intuition behind ReFT is that we would be able to establish the causal roles of hidden variables in neural networks, like in transformer models, and then we would fix the representations to the value that they would have taken if some counterfactual input was to be processed. And then we perform this distributed interchange intervention using this equation. So I'll go over this in more detail once we get back to the paper. Yeah, go ahead.
Hello, just a quick question. It might not be the right place to ask this, but I was stumbling over this equation, and the R is a linear transformation, right?
Yes, yeah, it's like a learned. It's, I believe, depending on the implementation, I think it's like a set of for this specific like low ReFT equation. This is a set of two matrices that are. It's similar to LoRa in a sense that it's down projecting and then up projecting.
I see. Because I was slightly confused, because R S minus RB would be R times S minus B, so the difference, right? So
yeah,
it rotates because they are orthogonal. You would expect these R and R dagger R to be identities, no?
Yeah, well, yeah, they say it's they're orthogonal matrices, but
it's still projecting, right? So it's essentially we're projecting B. We're taking the difference of the S and B and try to move it as this low rank of a matrix into something that resembles B, I guess. S.
Yes. Yeah.
Yeah. Okay. Thank you.
Yeah. So yeah, as you pointed out, is basically this diagram kind of explains it, which is we look at the high level and maybe make it a little bit bigger. So yeah, we take the hidden representations. We've got the they talk about this as the learned projected source, which is because they cannot establish a counterfactual example, which would be like the source. They learn it using this weight plus the hidden representation, or rather, yeah, multiplication of those two, the product. And yeah, so the actual edits, they then happen within this restricted subspace, as opposed to on the actual representation itself. So they can be more restricted in how they make the edits. So I go back. And in terms of training and inference and performance, so we keep the model parameters as frozen, and then we would learn these interventions that are then performed on the hidden representations of the model. So memory would be negligible overhead, and speed would be much faster. What's really interesting is that it requires very little examples to actually adapt the representation during inference towards some tasks. So like they have an example in the library which allows you to tune the model to respond only with emojis. And I think it's only like 10 examples that are required to fully adapt that model to only respond with emojis, which is really impressive. So, compared to something like thousands of examples that you need for LoRa or Dora, it's only 10, and it's really, really, really quick. In terms of inference, the speed slightly slower than full fine tune, and memory, there's minor overhead over the base model. It's kind of interesting about the performance because they've shown state-of-the-art results on some benchmarks, but only with handpicked hyperparameters, and they're claiming that there is a lot of these hyperparameters are still unexplored, so they encourage other research on this. And they've also found that the model is not very good at arithmetic reasoning, regardless of how they would train it. So I guess that's the outcome of this. So yeah, we've gone through the motivation for this paper. We talked about the adapters, the LoRa, Dora, any prompt-based methods such as the prefixes, and then they introduced ReFT, the idea of causal abstractions, the high-level models that map to low-level variables, the distributed interchange interventions, which is essentially this. So here we have the hidden representation, and then we would look at the counterfactual input. So yeah, I guess here this is the explanation that you mentioned, which was what is R? It's a low-rank projection matrix with orthonormal rows. So it's not a fully orthogonal matrix, I believe. It might only have orthonormal rows.
Yeah, that makes sense. Yeah.
Yeah, and they propose two, I guess, two flavors of ReFT. So the first one is the low ReFT, which is the low rank version of ReFT, which follows very closely the idea of the distributed interchange intervention. It's not exactly the same, but it's somewhat similar. And they don't really explain very well what the learned projected source is and how they obtain it. I believe it is being sort of discovered as the model is being trained. The learned parameters, so there are the learned parameters, so R, W, and B. And then the next one is the ReFT, which basically just removes this orthogonality constraint and this difference operation. So it is mainly done to reduce the training time. They did some ablation studies with later on showing like how that's different from ReFT and also the other methods that they benchmark against. An interesting note about this ReFT is it sort of resembles LoRa and can be thought of as LoRa directly applied to hidden representations, but only at certain positions in the input. Training objective, and they minimize cross-entropy loss as kind of the training objective for autoregressive generation. Yeah. They also do some experiments with classification, but I think this is kind of a softmax. Yeah. We'll talk more about what the interventions are. Yes. So they look at, this was about the positions. So not all of the positions in the input are affected. So they are quite selective about which, I guess, tokens within the input sequence are being targeted. They don't really explain very well how. I think they're kind of arbitrary, from what I understood, which is interesting, but again, underexplored in terms of research. And then they talk about the experiments, which is they've done some quite good experiments, I think, and quite extensive. There's more than 20 data sets that they looked at. They looked at both masked and autoregressive language models. And here they talk about the positions and how they intervene on them. I think it's only the prefixes and then suffixes of the input sequence that they look at, and they ablate on the how many positions from the right and then how many positions from the left. So they kind of split the evaluation based on the types of tasks that they would fine-tune towards. So for common sense reasoning, I think they achieved state-of-the-art, whilst being a lot more compute efficient. And then ReFT, which is the one without the orthogonality constraint, was only like slightly worse in terms of performance than ReFT. For arithmetic reasoning, that was the interesting one, which was that both ReFT and ReFT did not perform very well. And they have some intuition as to why. They think that ReFT may have more trouble on the chain of thought reasoning than as kind of a single step common sense reasoning. And that's because of the length of the generations. So if we have longer generation, then that means the effect of the intervention is reduced. So this kind of intervention on the hidden representations is only really effective on lower length generations of the model. Instruction following, that one was quite good, I think. I think they were mostly winning on both across majority of the other methods. And natural language understanding, similar. That so ReFT is a better choice when the language model is small. So that's what they discovered from the experiments. So yeah, there are some limitations. They mentioned that these capabilities were not explored fully. Then they also do a little bit of an experimentation in the appendix, looking at whether they could compose these interventions in various ways. So maybe they have interventions that make the model respond with emojis, but only in a sad way, which is another intervention that they may be able to learn. They talk more about how this work is situated, and then yeah, it's a different approach to both interpretability research, which kind of allows you to learn these interventions as opposed to find them manually and then test them, but also it's an interesting approach to fine-tuning. So yeah, overall, I think a really interesting paper, quite well written. I think it's currently under review. So this is only on Arxiv at the moment. And yeah, I really like the fact that they released the library to be able to play with these things. Yeah, that's all from me. So we could, any questions, any sort of discussions that you may have about this?
Thank you. That was, yeah, you're right. It is a very interesting paper. I need to dig into the maths more to be able to ask any decent questions, I think.
Yeah. I just thought it's quite cool that it turns out that the representations of the models carry a lot of the concepts as opposed to the neurons themselves. So like as opposed to the weights.
Yeah.
Which, yeah, quite an interesting outcome of this research. Julian?
Could you go over again some of the, by the way, was very, very interested. I'm extremely interested in all these aspects of LoRa, fine-tuning and so forth. But could you go over again some of the aspects you think that it will do best at? You and they have fairly mentioned problems with maths, which sounds like it won't be so great for helping with coding. What would we use this for in a best case?
Yeah, that's a good question. I think the limits on the the generation length. So I doubt we would be looking at so very long generations like the recent, say, the so recent OpenAI models, which are really tuned to respond in lengthy ways, and even look at their own like analyze their own outputs to be then perform better. So I don't think that would be the best I guess place to put this approach, but maybe something like GraphRag, where we are trying to extract specific sort of specific entities and relationships between entities in some like passage of text. I feel like this would do quite well.
Oh, that's very interesting. Very interesting GraphRag. So it sounds like if this were part of a larger agent or mixture of agents approach, it could be quite useful. It shouldn't be the big controller, as it were.
Oh, definitely not. I think, yeah, you're very right on the idea that like if this was part of a large agent, this has the advantage of being able to be fine-tuned within a few minutes as opposed to hours.
Oh, this is
very limited data sets. So like again, that emoji example that they provide, I think there's only like 10 or I think maybe either 10 or 16 examples that they have. And then you can pretty much pipe any text into that model and expect it to respond with somewhat applicable emojis to that text, which is really interesting. That the fact that you can have that much intervention on the model outputs with so little examples.
In going with what you just said there, with this idea of the sort of near instant fine tuning. An amazing use would be basically dynamic learning, dynamic correction, which has been a nightmare problem always. And it's, I don't know of any solution to it, but instant fine tuning seems to me to be a possibility, which would have huge consequences for all kinds of things, but for correcting not very good ASR, for instance, but also for robots. Robots are going to need to learn. And like we do, like, if you stick your hand in something hot, you better learn quickly that hurts. Whereas you can't go back and spend 4 months retraining the whole darn thing. So you need things. So this to me seems to be like the standout possibility for it.
Yeah, I agree. Yeah, definitely. The short fine-tuning time and the fact that we don't need to modify the actual model weights. We don't even we don't even create adapters for the weights. We simply modify the representations that are produced by original weights.
Yeah, on the fly. Very interesting.
Yeah. Yeah. Just looking through the appendix to see if I think they had a few examples of some of these outputs. I have a lot more sort of results on the ablations. Multitask learning. Yeah, so this is what they were trying to explore with these composability of these interventions, which is quite cool. So this would be like the German completion subspace that they had fine-tuned the low ReFT for, and then they had the instruction following in English, and they can obtain a combined subspace that basically does instruction following but in German, which is quite cool. So again, further, I'm pretty sure you can do that to some extent with regular LoRa. There's a way to compose adapters, but I don't think it's as intuitive to compose these adapters with LoRa because we're looking at the weights as opposed to the representations.
Right. Yeah, that's very interesting.
But it might be easier to do it in representations than it is in weights.
Great. Well, thank you.
Thanks a lot. Any other comments? Cool. Well, thanks everyone for coming to the paper club and sort of listening me talk about this paper. Yeah, and encourage you to come next week as well. I think it will be Gerard presenting.
Thank you for digging into all the detail and sharing it with us. This is yeah, excellent. So thank you.
Thank you very much.
Cheers.
Thanks again.